one is just adjective and the other one's not.
So we have a sporting goods store, and let me zoom this in a little bit. A sporting goods store has 3 stores in different towns. They want to have a distribution center equal distance from each of these stores. Right now, where my dot is, does that look like it's an equal distance? No, that does not look like an equal distance. But we're going to find how to make that an equal distance. Yes, ma'am. As long as you have your computer, and then it's on YouTube. Okay. Yep. So, yesterday we did constructions. And in our constructions, one of them, we were able to find an equal distance away from the corners of a triangle. Which construction was that?
The perpendicular one.
The one where we use perpendicular bisectors, which is the first 4 problems, which was what? Circumscribing. Because if we draw a circle that hits all 3 of these stores, then what happens is our circumcenter, our center of that circle, would be an equal distance away from each of those stores. Now, does it look like it's correct right now?
No.
Where should it go, do you think? Down a little bit. So we're going to throw the distance on here. Boom. Right now the distance is 8, 8, and 11. So it should be down a little ways. But where should we do it? Well, to figure out where we should do it, we should draw a triangle. I love it when you actually say the right answer right off the bat.
Yellow dark.
So, we've got this obtuse triangle going on here. So if I have an obtuse triangle, if I draw an obtuse triangle and I'm trying to find the circumcenter, where's the circumcenter going to be probably? Obtuse. It's going to be on the outside. So, as Mia said, we have to draw perpendicular bisectors. So we go more than halfway across.
I can't see.
Well, you'll see it in a second. Okay? So there's going to be one perpendicular bisector. The top one, the top line of the triangle. Okay? And boy, I'm close with that dot right now. Okay? Now, I'm going to bisect the bottom one. The reason why I'm not doing the left one is because my compass is so big, that line's just too short to be accurate with it. So I'm going to do the bottom one. No, I did the top line. So to do the bottom one, what I want to do is I want to see if I can go the same distance so I can reuse this one. And then go like this. And I'm going to do that angled one there. So if I do the angled one here, from here to here, it should be down here where I'm equal distance. So now if I move that point down to there, that's pretty close. If I go just a little to the left, no, a little to the right, and a little up, what should they probably be from each store? 9. It should probably be 9 from each store. Okay? But I mean, I can't get it perfect, Ella. I'm sorry. I'm not perfect. Now, maybe you can get it perfect, but I can't. Okay. So that's applying what we did yesterday to a situation that could come up in real life. You want to be an equal distance away from 3 points. Well, that would be the circumcenter of a triangle. All right. So, boom. So get out your vocab sheets, please. Okay. So, when we circumscribe a triangle, we're using perpendicular bisectors. Now let's look at this triangle without visiting with each other. Let's look up here. When I circumscribe, find the circumcenter of a triangle by doing my perpendicular bisectors, each of these lines is the same distance away from the circumcenter, right? That's why it's a circumcenter. Now, what do we notice about triangle ABP? What type of triangle is ABP? Besides obtuse, not a right triangle, isosceles, because it has 2 congruent sides. What do we know about triangle BP, whatever this is, C, BPC? That's isosceles. What about APC? Isosceles. Okay. What do we know about AJP? That's a right triangle. If you know 2 sides of a right triangle and you want to find the third side, what do you do? It's in the front of the room somewhere. The Pythagorean Theorem. You will have 2 Pythagorean Theorem problems today. Okay, you will have 2 problems that you have to work with the Pythagorean Theorem today, where you have to find a certain side. If you're finding the hypotenuse, what letter is that? C. The hypotenuse is C. The other 2 legs are A and B. Okay, so few vocab words right here. When 3 or more lines are intersecting in one point, which we have when we have circumcenters and incenters, they are said to be concurrent. So concurrent is when 3 or more lines intersect at one point. Vocab sheet?
Wait, does that mean like they meet at a point or at
they
one
meet.
point in the line?
No. They all meet in the same spot.
Okay.
Like a circumcenter.
I meant to like in the future eventually they'll touch.
Yeah, we'll have more. We'll have what are called orthocenters and centroids. Yep, too.
I never got a vocab sheet. I was going.
Okay. I will grab you one.
Yeah, I need one too.
All right.
I need one too.
Brandon. Thomas, why are you here? Oh, who said that they needed one but they were here?
Yeah.
You were here? Oh, right. Silly, right?
Maybe print another vocab sheet. Let me print one really quick because it won't take me long. Freeze this. Then go to Word. Find my vocab.
I'm liking this vocab sheet because I can write things. Shut. Take them. You can have.
Oh.
Yeah, I got all of those.
What's that?
It's for
Oh, I see. What do you do?
Okay, so where three lines come together, the lines are said to be concurrent with each other because they come together. The point where they come together is the point of concurrency, and we're going to have 4 points of concurrency this chapter. Circumcenter, which is the center of a circumscribed circle, the circle that goes outside a triangle. We're going to have an incenter, which is the center of an inscribed circle, okay, a circle that touches each side of a triangle. We're going to have an orthocenter, which is the point of concurrency of 3 altitudes. And we're going to have a centroid, which is a point of concurrency of 3 medians of a triangle. And we'll talk about medians and altitudes next week. Okay? All right. So, a circle that contains all 3 vertices of a triangle is called a circumscribed circle. That was your first 4 problems from yesterday. The first 4 problems on your constructions were all circumscribed circles, circles that went around the outside of a triangle. Okay? And because their radius is the same, that's how you get an equal distance away from the vertices of a triangle, is finding the circumcenter. Okay? So, there we go. The point of concurrency of perpendicular bisectors is the circumcenter. Point of concurrency of perpendicular bisectors. Okay, so if we look at this next picture, we have a hospital, a school, and a rec center. And they want to put an emergency siren so it's the same distance away from the rec center, the hospital, and the school. Where should it go? In the middle of here? No. Where should it go? At point E. Because point E is the circumcenter. So it's the same distance away from the hospital, the rec center, and the school. It's equidistant because it's the center, because it's where the perpendicular bisectors, and these are perpendicular bisectors, two sides, where they cross will be the circumcenter. That's the same distance. No, we're not talking about the grocery store. Grocery store doesn't have anything to do with the problem. Because it's just labeled in the problem. Yeah, well, they want it between those three. Okay. Where this stuff can get a little bit more difficult is when they give you coordinates and you have to find the circumcenter, incenter, orthocenter, things like that. Okay. Now, perpendicular bisectors, when you have horizontal and vertical lines, are really easy to draw. Okay? Because a perpendicular bisector, what does bisector mean? It crosses it at its
Point.
What kind of point?
Midpoint.
Midpoint. Okay? Crosses at a midpoint. What's halfway in between 0 and 4? 2. So if you make a perpendicular bisector at 2, it's right there. What's halfway in between 0 and 3? 1.5. If we cross it right there. What is the point of the circumcenter for this problem? 2, 1.5. 2, 1.5. Okay? All right. So that's circumcenter. That's circumcenter. Now let's look at incenter. Okay? Now, what do we notice about the incenter? It's inside, and it's also the same distance from the vertices? No, to the sides of the triangle. Okay? That's the big difference between incenter and circumcenter. The circumcenter is the same distance away from the vertices. The incenter is the same distance away from the sides of the triangle. Okay? That's what an incenter is. Notice how we have more right triangles. Okay? But we don't especially have isosceles triangles with this one. No isosceles triangles. Well, yeah, no isosceles triangles going on with this one. But we do have right triangles. Okay, more vocab. A circle that intersects each side of the triangle in exactly one point. You don't have to write down and has no points outside the triangle. Just the circle that intersects each side of a triangle at exactly one point. Yes, question.
Nothing.
Okay. And then the point of concurrency of the three angle bisectors is called the incenter. The point of concurrency of three angle bisectors is the incenter.
Why are you staring at me like that? Kind of sucks.
All right, continuing on.
Mr. Bridgewater, can you go back to the last one?
The incenter.
Whoa. You're smart. Did you hear what he did? Did you hear what I
Man,
said?
this is not a bird.
He told me.
I had no idea.
But did not say freak.
It's like when Jill swore in front of you that one time.
Hey,
That's a little rude. I think someone deserves some attention.
A little timeout.
I think you just zip it, and then nothing would happen.
Well, you shouldn't have said it anyway.
You should not have said it. That's not appropriate.
He was staring at us.
So I told him, why are you staring at me like that?
Why? And he said a naughty word.
Uncomfortable disaster.
Okay, so when we have an in-center, it's the same distance away from the sides, right? So what would we do with QP and RP to figure out the radius of the inscribed circle there? Not measure it. Oh, Tayton, you're making it way too hard. Look at this. Set QP equal to RP to find the radius. 3 times x plus 1 equals 5x minus 3. Okay, left side, first thing that we do, Olivia Meehan, is what? Combine them. How do we say we combine them? Distribute, Amaria says. Ella, what do we do next? How? Subtract 3x. Because you move the smaller variable first. Because you want to get the variable alone, so then it sets you up to figuring it out easier. Okay. Now what do we do? Add 3. So 2x equals 6, divide by 2. X equals 3. So is our radius 3? No. Gotta plug it in. 5 times 3 is 12, or 5 times 3 is 15, minus 3 is 12. The answer is 12. No. Okay. JLP is 32. We know JKL, this whole thing here, is 86. We want to find PJL, this half of a 1 here. Okay, so to do this, we know this is 32 for this half of a 1. What's the other half? 32. Okay, it's an angle bisector, so these have to be both 32. Now, 32 and 32 add up to? 64. So this whole angle is 64. This whole angle is 86. Add up 86 and 64, we get 130, which leaves 50 for this one out here. So we want just this half of the angle, which is 25. Oh, yeah, it's 150 over there. So this is 30. All right, so we're at 15. Mr. Bierschbach's full of screw-ups today. Illy will be dancing up and down, cheering. All right, so that's what we're doing today, working with that. We will have a couple right triangles where we have to figure out the Pythagorean Theorem. So there's a little bit more to this assignment, so do your best on it.